If we could distill this mysterious substance, what would we see? We'd probably see ancient Greece and Aristotle, who was the first person to write down what he called the laws of thought, or what we call logic. Now, the essence of logic is that it divides everything in life into two categories. Is it this or that? Heads or tails? Good or bad? Black or white? It must be one or the other. There are no shades of gray in logic. True or false? Yes or no? On or off? Which is where the computer comes in, because its circuits must also be either on or off. The other important thing about logic is the logical argument itself, which goes something like this. All tall men are thin. Jim is a tall man, therefore Jim is thin. If the first two statements are true, we can be absolutely certain that the third statement is true. On the other hand, if there are some tall men who are not thin, then we can't be sure that the third statement is true. And in black and white logic, if we can't be sure that it's true, then it must be false. Which is where the computer comes in again, because this is precisely the sort of argument that an electrical circuit likes to deal with. If we imagine one of these circuits as being like this, with a power source, a battery, two switches, and a light bulb, then we can see that the electric current from the battery can only reach the light bulb and make it light up when both switches are on. If either switch goes off, the light goes out. Now, as far as the circuit is concerned, on or off can just as easily stand for true or false. So if the first switch is statement 1 in our logical argument, and the second switch is statement 2, and the light bulb is statement 3, then only when both of the first two statements are true can the third statement also be true. But if either of the first two statements is false, then the third statement must also be false. What all this boils down to is that a computer is not a calculating machine. It's a logic machine. It doesn't so much compute things as argue about things in a strictly logical black and white fashion. Is one of my circuits on or off? A sequence of several ons and offs in various combinations can represent any number or letter or graphic symbol, and we can symbolize these ons and offs by using a 1 to stand for on and a 0 to stand for off. Most computers can represent any of the symbols on their keyboards by various combinations for a total of exactly 8 ones and zeros. Since this language or code is based on 2 digits, 1 or 0, just as a bicycle is based on 2 wheels, or a biplane is based on 2 pairs of wings, it is called the binary code, from the Latin word binarius, meaning 2 together. And each of the ones and zeros is called a binary digit, or bit for short. So it takes 8 bits to represent any keyboard character. Such a group of 8 bits is called a byte. 1 byte is the equivalent of 1 character. This computer can store or remember roughly 32,000 bytes. That means you can feed a program into it that uses up to 32,000 characters, letters, numbers, or graphic symbols. Just as a kilometer is 1,000 meters and a kilogram is 1,000 grams, so is a kilobyte roughly 1,000 bytes. This computer, therefore, has a 32 kilobyte memory, or a 32K memory for short. But the memory of most small personal computers can be extended to at least double that, 64K. This may sound a lot, but it isn't. The average page of a book contains about 2,000 characters. It's a 2K page. So even a 64K computer can only store as many characters as a 32-page book. And a 32K computer only as many as a 16-page book. Although, of course, A computer can do a lot more with its characters than a book can, but that's another story. Electric current travels through the computer's circuits at very close to the speed of light, 300,000 kilometers per second, which is about 1 billion kilometers per hour. If an astronaut were able to travel as fast as that, he would be able to go to the moon and back in just under 4 seconds. 1, 2, on the moon, 3, 4, back on Earth. So, since just one chip inside the computer can contain many thousands of electric circuits, and since chips are so small that you could fit 25 of them onto a postage stamp, you can see that it's quite easy for an electric current to make the rounds of all the computer's circuits in a few billionths of a second, and thus enable the computer to perceive many millions of different on-off switching patterns in 1 second. But it's very difficult for us to grasp what all this means, since our perception of time is so completely different. Here's a familiar example. This appears to be a moving picture of a horse and rider, but it isn't. It's a series of still pictures, which are being projected at the rate of 24 frames per second to give us the illusion of continuous flowing movement. The illusion works because the human eye cannot perceive anything that lasts for much less than 1/24th of a second. If we painted every 24th frame of this film black, we'd only just be able to glimpse it at normal film speed, because it would only be on the screen for 1/24th of a second. This is just about the limit of our perception of time. If it comes in chunks much smaller than 1/24th of a second, it scarcely exists at all as far as we're concerned. For example, if we could speed the film up to, say, 48 frames per second, the black frame would disappear altogether. In fact, for most purposes, our everyday life is divided into hours and minutes and seconds, whereas the computer lives in a world of thousandths of a second, milliseconds, millionths of a second, microseconds, and billionths of a second, nanoseconds. If the computer could see us, to its eyes, we would appear to be moving about as fast as a lump of rock. And the second or so that it takes us to decide which key to press next would seem like a delay of 7 or 8 years. Of switches that can either be on or off. When we feed messages into this maze of switches, what we're doing is getting them to form various temporary patterns of ons and offs in the computer's memory. But we can't do this to all the switches, because some of them have already been organized into preset patterns before the computer leaves the factory. These switches are stuck, and they consist of permanent instructions on how to load programs, how to print things on the screen, and so on. The computer can read this left half of its memory, but it can't write on it. It can't change it. It is therefore called read-only memory, or ROM. But the computer can, in a sense, write on the other half of its memory. This half is called random access memory, or RAM. Because the computer can write temporary messages anywhere it likes here, it has random access to this part of its memory. But if you switch the computer off and then on, the messages in its random access memory disappear. The loose switches are scrambled once again, whereas the instructions in the read-only memory stay as before. The switches are still stuck in the same position. Of course, you don't necessarily have to program messages into RAM yourself. You can load a ready-made program full of messages into it from a cassette or a disc. You can take the cassette or disc away and the messages will remain. But naturally, if you turn the computer off and then on, once again, the messages will disappear. But at least you've still got the originals on your cassette or floppy disk. So ROM is read-only memory, and it's permanent. It never forgets. Whereas RAM is both read and write memory, and it's temporary. It forgets at the flick of a switch. The computer is rather like a little office which has two hatches. You feed information and instructions into the office through the input hatch, and the results of your instructions are dished out to you at the output hatch. Inside the office is a very literal-minded clerk who can only carry out one very simple instruction at a time. He is called Central Processing Unit, or CPU for short. CPU has access to two little boxes. One is called ROM, which stands for read-only memory, and is filled with permanent instructions on how to do his office work. And the other is called RAM, which stands for random access memory. And this is where CPU holds whatever information or instructions that you care to give him from time to time. For example, some instructions like this, CPU will put straight into his RAM box and then go away and mark time until you give him the command run. CPU will then return to the RAM box and read the first instruction, which tells him to print something. CPU promptly nips across to his ROM box and looks up how to print. Then he prints something and gives it to you at the output hatch. Next, CPU trots over to his RAM box again and reads the next instruction, which contains the command go to. Back to the ROM box to find out how to go to, then go to instruction number 1 in the RAM box, which tells CPU to print something. Then it's over to the ROM box to find out how to print, because CPU has forgotten already. Then he prints something and gives it to you at the output hatch. Then back to the RAM box to read the next instruction, which contains the order go to. Of course, he's forgotten that, so over to the ROM box to find out how to go to. Then go to instruction number 1 in the RAM box, which tells CPU to print something. Then back again to the ROM box to find out how to print, and so on and so on and so on. The only thing that keeps this dim-witted little bureaucracy in business is that CPU moves with lightning speed. So fast, in fact, that he can give you the illusion that you're dealing with a very clever outfit indeed. You no sooner ask for something than it's done. The naive reality behind this illusion is hidden from you, because all that this office consists of is CPU and his two memory boxes, ROM and RAM, and the input and output hatches. And that's all that any computer consists of. And even this can be reduced to 3 basic elements when you come right down to it: input, output, CPU, and memory. If you ran out of milk, all you'd have to say to even quite a young child is, "Please fetch me some milk." Give them the right change, and sooner or later you'd get your milk. But if you had to get a computer to run errands for you, it would be a different story. Unlike the little boy, it wouldn't know where to find milk. So first of all, you'd have to tell it to go to the nearest corner store. But of course, it wouldn't know what to do when it got there. So then you'd have to tell it to look for the milk in order to be able to answer the question, is there any milk in the store? But even if the answer were yes, the computer still wouldn't know what to do next. You would have to tell it to buy some of this milk and bring it home. And if the answer to the question, is there any milk in the store, were no, you'd have to tell the computer to go to another store and look for the milk in order to answer the question, is there any milk in the store? If yes, buy some and bring it home. If no, go to another store, etc., etc. If there happened to be a shortage of milk in your neighborhood, the computer could find itself caught in an endless loop, going from store to store ad infinitum. This is the first basic operation performed by a computer program, repetition.
And here is the second basic operation performed by a computer program. Yes, no decision. The inner workings of all computer programs, however complicated they may appear on the surface, are all variations on these two basic themes: repetition and decision.